Suppose you have a set that has n elements. Let's say a set S that has n elements. How will you demonstrate that it indeed has exactly n elements? It might be helpful to consider a real world situation. Say somebody hands you over a set of 500 rupee notes and says that there are 5000 rupees in net in these notes together. How do you check that? Well, you start riffling through the notes one by one, saying 1, 2, 3, 4, and the number you assign to the very last note is the number of notes that are there. In short, what we are doing is, to each note we are assigning a unique number starting from 1, and the ending number is supposed to be the number of elements. From this real world analogy, the following proposition is very easy to prove rigorously, and I leave it to you to prove that. The proposition says the following: a set S has exactly n elements if and only if we can find a bijection f from 1, 2, 3 ... n, the set consisting of the first n natural numbers, to the set S. This is analogous to just pointing to the first element and saying 1, pointing to the second element and saying 2, and pointing to the very last element and saying n. Okay, so we have this following definition that comes. Definition: a set S is said to be finite if it has n elements where n is in natural numbers union set with 0. A set is said to be infinite otherwise. So finite sets are those that have n elements for some natural number and 0. So the empty set which has 0 elements is considered a finite set. An infinite set is one that is not finite. Now we have this easy exercise. Show that a subset of a finite set is finite. Also show that superset of an infinite set is infinite. This exercise is very straightforward. Please solve it. The next proposition that I am about to prove is also utterly obvious, but there is an idea in the proof, so I am going to present the proposition. The set n is infinite. The proof is very easy, but there is a worthwhile idea to remember. We have to show that you cannot find a bijection from any set of n elements to the natural numbers. What you do is you consider a map f from 1, 2, 3 ... n to the natural numbers. Okay? Then set m to be the maximum of f of 1, f of 2, so on, f of n plus 1. Okay? Then it's clear that m has no preimage. That means f cannot be surjective. What we have shown is any mapping from an n element set to the natural numbers cannot be surjective. Therefore, n is infinite. The next proposition is also not that hard, but it's a little counterintuitive. Proposition: a set is infinite if and only if it contains a proper infinite subset. Okay, how do you prove this? Well, it's an if and only if statement. So there are two directions to prove. The fact that if a set contains a proper infinite subset, then the set itself has got to be infinite, just follows from the last exercise that I have given you, that the superset of an infinite set is always infinite. Okay. So now I will prove the other direction. I will assume, suppose S is infinite. I have to produce for you a proper infinite subset. How do I do that? Well, it's very simple. Let S1 be some element of S. Consider S minus S1. Removing one element from an infinite set is suddenly not going to make it finite. How do I prove that? Well, suppose you have a map F from 1 to n to S minus S1 that is bijective. Suppose you are able to find a map like this. Then the map F extended to, let me just call it F tilde, extended to n plus 1 to S, where it's defined as F tilde of k is equal to F of k when k is 1 to n, and F tilde of n plus 1 equal to S1. This map is clearly bijective. Okay. So what this shows is that if you could find a bijective map from S tilde minus S1 to, if you could find a map F from 1 to n to S minus S1, then you can find a bijective map F tilde from 1 to n plus 1 to S, which is not possible. Therefore, S minus S1 is infinite as required. So infinite sets are those that have an infinite proper subset. Okay. I'll give you another exercise that immediately follows from our discussions. Exercise: show Z and Q are infinite. This just follows immediately from our discussion. In fact, it follows from the previous exercise quite easily. So for finite sets, I can define a notion called cardinality. That's as follows. Definition: let S be a finite set. The cardinality of S is the number of elements. Usually we denote cardinality like this. We put a modulus sign of sorts. Now the question arises, can we define a cardinality for infinite sets? We can, but things are a bit tricky for infinite sets. Let me first, before we discuss this in greater detail, prove that any infinite set is is at least as large as the natural numbers. How do we make that precise? We have the following lemma. A set S is infinite if and only if we can find an injection F from N to S. Okay. Now, one part I'm going to leave it to you to show that if indeed you can find an injection from the natural numbers to the set S, then the set S has to be infinite. That part I leave it to you. Now I'm going to show that an infinite set always admits an injection from the natural numbers. How do we show that? We define F inductively. How is this done? Well, you first pick an element S1 in S. It could be any element, it doesn't really matter. Set f of 1 to be S1. Okay. Now the set S minus S1 is infinite. That's just what we showed in the last proposition. So you can pick S2 in S set minus S1. We can pick an element S2 from the set S with S1 removed. Then set f of 2 to be S2. Okay. So inductively, suppose you have chosen f1, f2 up to fn, set fn minus fn plus 1 to be some element in S minus f of 1, f of 2, ... f of n. Pick any element. Okay. This gives the required injection. So inductively define the map to ensure that each stage it is injective, therefore globally also it's injective. Required map. Okay. Now we come to a mind-bending theorem. It's an important theorem. I like to call this theorem the whole is not always larger than the part. What does this theorem say? A set S is infinite if and only if it is bijective to a proper subset. Okay. So the theorem says that infinite sets are those that are in themselves bijective to a proper subset. Now we have already seen that if you remove a single element from an infinite set, you still get an infinite set. This theorem sort of extends that to a much more powerful result. Proof. Before I present the proof, let's just remark what we have to do in this set, particular theorem. We are given a set, we have no further data about that set other than the fact that it's infinite. From that we have to manufacture a subset and a bijection. This seems like a hard task. So what we do in such situations, and it's generally a good idea to do this, is to first concentrate on a particular case. Fix S to be a particular set which is infinite and try to prove it in that case. In this scenario, in this particular theorem, what happens is that particular case itself gives you the full proof, but usually that doesn't happen. But at the very least, what happens is when you show a particular case, you get an idea of how to treat the general result. So what we will do is we will first consider n, the natural numbers. Okay. Now we have an obvious bijection G which takes n to n plus 1. Okay. This maps the natural numbers bijectively to natural numbers minus the set with one element 1. Okay. So we have managed to solve this theorem in the special case when the set is the natural numbers. Okay. How do we deal with the general case? The previous lemma gives us f from natural numbers to S an injection. We get an injection from the natural numbers n to the set S. Now what I do is I define H from S to S set minus f with 1, f of 1, the image of 1. How do I define this? I define this in the following way. H of x is defined to be equal to x if x comes from S minus the image of the natural numbers under the map f. So if f of if you take a particular x which is not in the image of the map f, just fix it, just take the identity there. Otherwise just set it to be f of n plus 1 if x equal to f of n. Okay. So what we have done is essentially we have defined the map H in two parts. On the set that is not hit by the image of f, you just leave it as it is. On the part that is hit by the image of f, you just move it to the side using the map G. So this map is injective because identity f and g are okay. Its image is clearly S minus f of 1. Every element other than the element f of 1 is considered is there in the image of this map. Okay, so H is the required bijection. H is the required bijection. So this concludes the proof. So infinite sets are those that are bijective to a proper subset. Okay, so this sort of says that defining cardinality for infinite sets could be a bit tricky. Now one guess would be that all infinite sets are bijective to each other. This particular theorem might suggest that. This is not true. This was shown by Cantor. Cantor showed that there are infinite sets that are not bijective. To each other. Not only did he show that, he showed that there are hierarchies, there are infinitely many different infinite sets, and that is the content of the next theorem. This is proved by Cantor. The theorem is as follows. Let S be a non-empty set. Then there does not exist a surjection from S on to power set of S. Okay. How do you prove this? The proof is an ingenious idea of Cantor. What you do is, suppose you have a map F from S to the power set of S. Okay. Now what you do is you define a special subset R of S defined as follows. R is the collection of all S in S such that S is not an element of f of S. Okay. You look at all those elements in the set S that are not present in the image. That means the image does not possess the element S. Okay. There must be, suppose this map is surjective, then we must have some f of R is equal to R for some R in R. Sorry, for some R in S. Okay. Now two possibilities can happen. The first possibility is that the element R is an element of the set capital R. That can happen. There are only two possibilities. Either the element R is a element of the set R or it isn't. If the element R is also an element of the set capital R, then this is problematic because f of R is equal to R and R is here. But the set capital R was defined precisely to be those elements which are not contained in its image. So this possibility is ruled out. This is not possible. The second possibility is the element R is not an element of R. Okay? But this means R is in R by definition. By definition, because f of R is equal to capital R. Okay? So the definition of the set capital R is it is those elements that are not contained in its image, and this is directly contradicting that. Okay? So both possibilities give a contradiction. That means F cannot be surjective. F cannot be surjective. So the power set of a non-empty set is always larger than that set. The smallest infinite set, the smallest infinite set, I'll put smallest in quotes, infinite set is the natural numbers. The smallest infinite set is the natural numbers. The cardinality of the natural numbers is defined to be this symbol called Aleph naught. Now to define what this is precisely will require a much deeper set theoretic machinery than what we have available. I'm just mentioning this in the passing. This is read Aleph naught, Aleph 0, and I'll try to write it correctly. It's a bit complicated to write it as it's Hebrew, I think. It's supposed to be written something like this. Something like this. Okay? Now, one more definition. Any set that is finite or bijective to the natural numbers is called a countable set. A set that is bijective to n is called denumerable. Okay. Now, denumerable sets by definition admit a bijection from the natural numbers to itself. Okay. So you can write the elements of S as f of 1, f of 2, f of 3, so on. This collection f of 1, f of 2, f of 3 will exhaust S. Why does it exhaust S? Because that's the definition. It's a bijection from natural numbers to S. Okay. Now I give you an exercise. Show that any set S whose elements can be listed S1, S2, ... is countable. Okay. Note that I am not requiring this list to have no repetitions. In the previous list, when the set is denumerable, when I write the set as f1, f2, f3, there is no repetition in the list. But here in this exercise, I am not requiring the list not to have repetitions. It can have repetitions, but the conclusion is weaker. The conclusion is that the set is countable. It could be denumerable, it could be finite. It really doesn't matter. Okay. With this exercise in hand, we can now end this session, this module on cardinality with a nice proposition. Proposition: countable union of countable sets is countable. Okay. Countable union of countable sets is countable. How do I make this precise? Well, if consider the collection of sets AI, where I is an indexing set, is a family of countable sets indexed by the countable set I. Okay. Then the set A, which I define to be the union of I in AI, this is also countable. Okay. Proof. Okay. First, consider A to be the empty set. In this scenario, nothing to prove. So we have disposed of with the trivial case that A is the empty set. So pick an element A in A. Okay. Now what we do is the following. There are two possibilities that arise. Either I could be finite or denumerable. Okay. First, let me consider the case where I is denumerable. I will consider the case I is denumerable. And what I will do is I take a map F from N to I, that is bijective. Okay. And define Bj to be just A of F of I. Okay. So these Bj's are a collection of sets indexed by the natural numbers. And not only that, the union of the Bj's is just the set A. Clearly, I have just re-indexed the set A with an index coming from the natural numbers. Now, what I do is, I look at B1 and list out all the elements of B1, which is possible because B1 is countable. B11, B12, so on. But this list could terminate. If the list happens to terminate, what I do is, I extend the list infinitely by just adding A's. I just keep repeating A's in this list. I do the same thing for B2. I write it as B21, B22, and so on. If the list does happen to terminate, I just repeat the A's. So I get an infinite rectangular array of elements coming from the various Bi's. Now I am going to list all the elements of A as follows. First I will put B11, then I will put B12, then I will put B13, then I will put B21, then I put B13, then I put B22, then I put B23, so on. So the procedure is clear. First list all those elements Bij where I plus j is 2, then I plus j is 3, then I plus j is 4, so on and so forth. Just list these elements in this order. It is clear that this list exhausts A. Every single element of the set A will appear somewhere in this list. Of course, there will be plenty of repetitions, but that is not a problem. From the exercise, any listing, if a set can be listed even with repetitions, it's going to be countable. Okay, so this deals with the case where I happens to be denumerable. If I is a finite set, if I happens to be finite, then we pull the same trick. We have a map f from 1 to dot 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 n to I, bijective. So you will get the sets b1 to bn. Well, then artificially enhance this list to have bn plus 1, bn plus 2, which are all just singleton sets A. Okay? Then repeat the argument we have given above. This proves the result even in the case when I happens to be a finite set, and the previous case dealt with it when I was a denumerable set, hence we are done. I leave you with one exercise. Show that Q and Z are countable. Okay, this is a straightforward exercise from what we have shown right now. In the next week's lectures on real numbers, we will see that the set of real numbers has in fact a different cardinality than the cardinality of the natural numbers. That means you cannot find a bijection from the natural numbers to the real numbers. This is the course on real analysis, and you have just watched the module on cardinality.